Ladies and gentlemen, welcome back to Lesson 7 in Group Theory. In this course, we talk about groups, and now we're going to be talking about what makes two groups look the same. So, to do that, we need to define what is a homomorphism, and afterward we'll give some examples on homomorphisms, and then we'll say that if a homomorphism respects certain properties, then it turns into an isomorphism, which essentially means that two groups become isomorphic if they're different, but they look exactly the same. For example, the dihedral group that is responsible for rotating and flipping a triangle is isomorphic to the symmetric group responsible for permutations of three elements. So we give the isomorphism by this sign, essentially saying that while these two groups are different, their structures are exactly the same. So we might as well replace each element of the first group by the second group. So let's get started. Let us now define what a homomorphism is. A homomorphism of groups is a map phi. By the way, we could use any symbol. So it's a map phi that takes an element from G, which is a group with an operation star, to H, another group with the operation dot, such that it respects the single property that is phi of G1 star G2 is equal to phi of G1 dot phi of G2. Let me write the dot properly. So here we have that G1 and G2 are defined elements in G. So this is for all G1 and G2 in the group G. So one thing to remark here is that the operation on the left-hand side here is an operation in G, and the operation on the right-hand side is an operation in H, because these two here are elements in H. So it's sort of like if you live in a country, you abide by its rules, but if you move to another country, you follow a different set of rules. So the country here being G, where the inhabitants G1 and G2 have to respect the operation of G, and on the right hand side they have migrated into H, where they have to respect the operation of H. So what this definition is intuitively saying is that a homomorphism respects the structure of both groups. So if when it takes the elements G1 and G2, it carries them into phi of G1 and phi of G2 in a way that respects the structure of both groups. So here we can see that G1 and G2 operating together on G gives the product G1, G2, and phi of G1 and phi of G2, the images of G1 and G2 by phi, when they operate together, we get phi of G1 times phi of G2, thus respecting the group structures of both groups. So in a sense, homomorphisms are maps that behave nicely with respect to the structure of the group. Okay, now that we defined what a homomorphism is, we'd like it to be even more respectful of the structure of the groups. So if the homomorphism has other certain properties that I will discuss now, we will give them even different names. So, for example, a monomorphism is a homomorphism that is injective. Injectivity is a property that you might have studied in discrete mathematics. It says basically that no two elements are mapped to the same element. So this, for example, is not injective, because we have that two elements on the left are mapped to one element on the right. The one on the right, however, if I draw it like that, where each element is sent to a distinct element in the codomain, this is injective. If you notice the drawing on the right, you would see that while it is injective, the poor element here does not have any pre-image to it. In other words, there is no element in the domain that is mapped to that poor element over there. So to fix that, we will add another property that we would like to have the homomorphism to have. And that property is surjectivity. So an epimorphism is a surjective. I should have used a different color for that one, but it's not the end of the world. Surjective homomorphism. In other words, for all H in the codomain, there exists an element in the domain G such that the morphism phi maps G to H. So there exists a preimage of H. So this, for example, is injective but not surjective. So it is not an epimorphism. So this one here is not surjective. And if we draw this one like this, for example, this is surjective. But as we've seen before, this is not injective. So we have now two nice properties that we've added, and now it's time to see what happens when we have both properties at the same time for a homomorphism. And now, if we have both of these properties on the homomorphism, we say that it's an isomorphism. So an isomorphism is a bijective homomorphism. In other words, we have that phi is both injective and surjective. In other words, for all elements H in H, and is also an isomorphism. In this case, G is isomorphic to H as groups, and we write G is isomorphic to H. In other words, if we have an isomorphism between two groups, we can say that they look exactly the same, and all what we can do is we can replace each element in G by an element in H, and we replace the operation in G by the operation in H, and we would not have changed the structure one bit. We have two more items in this definition. The first one being if G is equal to H, that means phi is a homomorphism that takes G all the way inside G, then phi is called an endomorphism. So it takes an element in G and sends it to another element in G. That is an endomorphism. So an endomorphism that is also bijective is called an automorphism. Special kind of endomorphism that if G star is a group, any group, the set of automorphisms of G, denoted by aught of the group G, is a group with its operation being composition. Composition of what? Composition of the automorphisms. In other words, if we had an automorphism sigma in aught G, and we had another automorphism tau, then we can compose them together to have sigma and then followed by tau. That is also an element in aught G. So it is closed with respect to the composition, and we have that any element in aught G has an inverse because automorphisms are bijective maps. And lastly, we have that the identity element exists, and it's just the automorphism that sends each element in G to itself, therefore making the set of automorphisms aught G into a group. Now this result is a bit surprising. Why is automorphisms of G make a group? Well, the set is a group because the operation of composition of automorphisms is an associative operation. There exists an identity element, which is the identity automorphism that sends each element in G to itself. And lastly, we have that each element, which is each automorphism in G, has an inverse because automorphisms are bijective. So it makes for a nice group. And this group is studied more in depth in field theory and in Galois theory. Two very interesting subjects that follow from the topic of groups. Now that we have defined what a homomorphism is, it's time for some examples. The first one being an example that is very familiar with you, the exponential function. Let us take, more formally speaking, the group R with addition sent all the way to the group R with multiplication. We have to take care here that the group R with multiplication is without 0 because 0 does not have an inverse. Okay, so phi here takes x and gives e to the x, right? And phi is in fact a homomorphism because for all x and y in R, phi of x plus y is equal to exponential to the power x plus y, but we can use the exponential laws that we know and love to separate the x and y's. We get e to the x times e to the y, and that is equal to phi x times phi y. Notice here that while the operation here is addition that respects the operation in the group on the left, this operation is multiplication that respects the operation on the group, the operation of the group on the right. And in fact, phi is not only a homomorphism, but it's also injective, making it a monomorphism. So for all x and y in R, if e to the x is equal e to the y, which basically means phi to the x is equal to phi to the y, we know that exponential is by nature a function that is injective, because if we apply the natural log ln to both sides, we will get rid of that e and we will have x is equal to y. So it is in fact a monomorphism. The last thing to say is that it is not an epimorphism because let's take, for example, an element that is not a positive element in Rx. So let's take, for example, -1 is in Rx, but we cannot reach -1 by doing an exponential because exponential function is always positive. So there does not exist an element x in R such that e to the x is equal to -1. Therefore, phi is not surjective, therefore it is not an epimorphism. So let us now look at the second example for homomorphisms. The second example may well be familiar with some of you. It is in fact just the determinant of matrices. So more formally speaking, let phi be the map that takes a matrix in GL2R. Remember, GL2R is the general linear group with order 2. So 2 by 2 matrix with coefficients in R, with the operation being matrix multiplication, and sends it to a non-zero real number with the operation being multiplication in this group. So the determinant is non-zero because the GL2R is defined to be the matrices that have a non-zero determinant. So let us prove now that phi is a homomorphism. Okay, phi is a homomorphism because phi of some matrix A times B is equal to phi is equal to determinant of A times B, but we already seen in lesson 6 of the course that determinant of AB is equal to determinant of A times determinant of B, and so we can just replace it back with the definition of phi. So that's phi A times phi B, and we have successfully managed to prove that it's a homomorphism. So remember, the multiplication here is matrix multiplication, unlike the multiplication in the right hand side where it's just multiplication of two real numbers. Next, we want to prove that phi is not a monomorphism. In other words, it is not injective. And to do that, we need to see that we have two matrices which are different but give the same result when you apply the determinant. So the two matrices are, for example, 4 and 1, 0, 0, and 2, 2, 0, 0. So when you take the determinant of both, you will find that, so the determinant of 0, 0, 1 and 2, 2, 0, 0, you find that the determinant of both is equal to 4. So the image is the same, but the two elements in the domain are different. Therefore, phi is not a monomorphism. Lastly, we will prove that phi is in fact an epimorphism. That means using the elements in the domain, we can reach all the elements in the codomain. All of the elements here are the non-zero real numbers. So that is in fact the case because for all x, a real number that is not zero, there exists a matrix which we will define as x, 0, 0, 1, such that the determinant of x, 0, 0, 1 is equal to our desired element in the codomain, x. So essentially saying that by using this matrix construction, we are able to reach all of the real numbers that are not zero. So we've now just seen two examples. One was a monomorphism but not an epimorphism. The other was an epimorphism and not a monomorphism. Now we will see an example of a map that can be both an epimorphism and a monomorphism, thus making the two groups isomorphic. In this example, we will revisit what we have seen before when we've seen the two multiplication tables. One was for the additive group of z for z, the other was the multiplicative group of z10z star. Just a reminder, z10z star are the elements that are just co-prime to 10, being 1, 3, 7, and 9. So after having the multiplication tables ready, we have noticed something. We have noticed that if we replace each of the elements, so if we replace 0 by 1, 1 by 3, 2 by 9, and 3 by 7, we will see that the group structure is preserved, and all what we're doing is changing the labels of the elements of the first group with the elements in the second group, and the labeling of the operation addition to multiplication. So this has the same exact structure, and we have deduced that this must be an isomorphism. And in fact, now we can formalize this by saying we will define phi going from z for z to z 10z star. So this is a map now that takes elements from z for z to z10z star, and phi of 0 is equal to 1, phi of 1 is equal to 3, phi of 2 is equal to 9, and phi of 3 is equal to 7. And we can prove that phi easily is a bijective homomorphism, therefore it is an isomorphism. Therefore, the groups z for z with addition is isomorphic to z10z star with multiplication. Essentially saying these two groups look exactly the same. Okay, this example now is wild. It's natural but unexpected. Consider the group S3, the symmetry group of 3 elements. Consider also the group of D6, which is the dihedral group of symmetries on a triangle, which has 3 vertices. These two groups are isomorphic. That means that they are exactly the same thing, except that elements are different and operation is different. This is what I'm going to be proving now. So D6 is isomorphic to S3. So let us write down S3 and D6 to get a better idea of what we're dealing with. So S3 is the group, again, of permutations of the elements 1, 2, and 3. So to write them down, we can write the permutations possible, which is identity permutation, the one that flips 1 and 2, the one that flips 1 and 3, the one that flips 1, 2, 2 to 3, 3 to 1, and that one that changes 3 to 2, 2 to 1. And I'm forgetting one, which is the one that flips 2 and 3. And with that, we have exhausted all the possibilities in S3, and we find that there are in fact 6 elements. Now, you might ask, does D6 also have 6 elements? Yes, it would, because if not, then it would be pretty bad news for us. Okay, so D6 has the elements 1, and all the other elements are generated in fact by R and S, and even 1 in fact is generated by R by having R to the 3 is equal to 1 in this case. So we would have R square, S, SR, SR square, where R is the rotation, which is done anticlockwise, and S is the reflection about the axis which passes through 1. So we have two different groups, but they have the same number of elements, and it's time to see if they are isomorphic. And if they are, what is the homomorphism that we can use, and how can we prove that it's an isomorphism? So first of all, recall that in lesson 4 of this course, we have seen that the group D6 is isomorphic to a group with the following presentation. The presentation would include two elements that generate the group, which we call A and B. Now we have that A and B generate the whole group with some specific relations, such as A cubed is equal to 1, B squared is equal to 1, and AB is equal to BA inverse. So if D6 is isomorphic to this group, that means that we need to see that S3 has also these relations if we choose a appropriate A and an appropriate B. So this is in fact what we're going to do. We're going to choose A to be some element here and B some other element there, and we're going to see that they satisfy the relation. So letting A be equal to, okay, so A cubed is equal to 1, so it makes me think that the element I want to choose must have some order 3, and the order 3 elements is either 1 to 3 or 3 to 1. I'm going to be choosing 1 to 3. And B squared is equal to 1, so it leads me to think that B is an element of order 2, so it could be 1 2, 1 3, or 2 3. I'm going to choose 2 and 3, and I will explain why I made these choices in particular in a minute. So we have 2 and 3. Okay, now it's time to verify that A and B satisfy the relations for the generators of that are isomorphic to D6. So A cubed, because this is an order 3 element, if we take the cube of that, we'll get the identity. So that's verified. B squared, likewise, because it's a 2 cycle. And lastly, we have that AB is equal to what? If we compose these 2 cycles together, we find that 2 is sent to 3, which is sent back to 1. So 2 is sent to 1. And 1 is sent to 2, so that's done. And 3 is sent to 2, and 2 is sent to 3, so 3 is just sent back to itself. So this is 2, 1. And let's check now BA inverse. So A inverse is equal to 3 to 1. And you can check that yourself. A inverse is 3 to 1, and we compose it with B to have 2, 3, and 3 to 1. And this equals to, in fact, 2, 1 again. And you can check that by yourself. So we have just found two elements A and B that satisfy these relations. Life is good. There exists a homomorphism, we call it phi, that goes from D6 to S3. Now, can we define this homomorphism explicitly? You bet. So here, how do you construct phi? Think about it. D6 is a set that contains the symmetries of a triangle. In other words, if you have a triangle with vertices labeled 1, 2, 3, like this, and you set an axis of flipping about 1, so the flipping is done in such a way that 2 and 3 are exchanged. So D6, it talks about the symmetries that move around the vertices 1, 2, and 3. So essentially, 1 and 2 and 3 are going to be moved around in places where they either are the same places or they're in a different place. So these changing of the vertices can be considered as a permutation of the elements of 1, 2, 3. So this is the reason why we consider 1, 2, 3 as the vertices of the triangle, but it's in fact the set on which we can perform our permutations, which are in fact in S3. So we can consider our homomorphism phi to send R and S to some certain permutation. So which permutation should we associate R and S with? So R remember, it's the rotation anti-clockwise. So when we rotate the triangle anti-clockwise, we find that 1 goes over here. So 1 is now over there, 2 goes over here, so 2 now is over there, and 3 it goes over there, so 3 is in this position. So essentially speaking, 1 goes to 2, 2 goes to 3, and 3 goes to 1. So we can label our R to be 1, 2, 3. And for S, we use a similar argument to say, okay, if we have a reflection about the axis, what will we obtain? We will obtain a reflection where 2 and 3 are flipped around. So 2 goes to 3 and 3 goes to 2. Wow. Okay, now we have symmetries that are related to their respective permutations just by assigning the vertices to the numbers. Okay, so now we can say for a fact that since the group of symmetries is generated entirely by just R and S, this definition that just handles R and S, it doesn't handle all the elements in D6. In fact, this definition is enough to describe the whole homomorphism, the whole map of phi on D6. And why is that? Because if we take any other element in D6, we will just find that it's a product of, it's some combination of R and S. So we can use some combination of 1, 2, 3 and 2, 3. So now that we have done our definition, we want to see that it is a homomorphism. And in fact, it is, because we've just seen that the same relations are satisfied over here, and you can check for yourself that phi of SR is equal to phi of S times phi of R. So on the left hand side, you will perform your symmetries on the triangle, and then you're gonna see where phi takes each vertex, and on the right hand side you're gonna perform just the cycle composition of 1, 2, 3 and 2, 3, and you're gonna check that they're equal, and you're gonna repeat the same process for RS, and you're gonna tell me what you get, and you must get something that is equal. So this is very, very good news. Now that we have proved that phi is a homomorphism, we notice that the order of these two groups, D6 and S3, are the same, and they're both equal to 6 because both groups contain 6 elements. So here we have that since phi is surjective and phi sends elements from D6 to S3, from a group of 6 elements to a group of 6 elements, then necessarily phi is also injective. So because of that, we have both surjectivity and injectivity to have what is an isomorphism between both groups. The reason phi is surjective is because all the elements in S3 can be generated by A and B. So the first element is 1, 2, 3, and the second element B is 2, 3, and you can prove that each element is a combination of these two elements. And with that, we complete the proof of this wonderful result that the symmetric group and the dihedral group are essentially the same. Before you prove that a map is a homomorphism, it is very important to check that the map is in fact a well-defined function that sends each element to a unique element. A degenerate case where a function might send one element to two elements is what we call an ambiguity, and we really don't want that to happen for the function to be well defined. To do that, we need to first prove that it is well defined before we prove that it is a homomorphism or injective or surjective or whatever. So let us see an example to see why this is so important. Let G be the additive group finite, which is Z12Z, and let H be the additive group Z3Z. And let phi be the homomorphism, be the map that goes from G to H takes an element from Z12Z, gives you back the same element but in Z3Z. So Z12Z, remember, they are the elements 0, 1, 2, so all the residue classes all the way up to 11. That's equal to Z12Z. And Z3Z is all the residue classes 0, 1, and 2. So let us see that phi here is well defined. We will perform this computation explicitly. So phi is well defined, meaning that if x1 is equal to x2 in the domain, then phi of x1 is equal to phi of x2. So let us compute the phi of all the elements in Z12Z and see what we get. So phi of 0 is 0, phi of 1 is 1, phi of 2 is 2, phi of 3 is 3, but 3 is equal to 0 mod 3, and 4 is 1 mod 3, 5 is 2 mod 3, 6 is 0 mod 3, 7 is 1 mod 3, 8 is 2 mod 3, 9 is 0, 1, and 2. So you can see that there is a kind of repetition going, 0, 1, 2, 0. So what is going on? Why is there such a repetition? Well, a very simple, logical, intuitive explanation for this is if I come back to our beloved clock. So in the clock, the interior, the pink, is our G. It's the Z12Z. And the exterior, the one that I wrote in blue, is our H, which is Z3Z. So our H is nothing but the elements 0, 1, and 2. So we can see here that for each quarter of an hour, we basically finish an entire round on H. So 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 0, 4 goes to 1, 5 goes to 2, 6 is 0, 7 is 1, 8 is 2, 9 is 0, 10 is 1, 11 is 2, and 0 is 0. So we have this very nice, well-defined map phi. And in fact, we can prove that phi is not only a homomorphism, but also an epimorphism, because epimorphism means that all the elements in the codomain can be reached by applying phi on some element in G. And that is in fact true because we've seen that 0, 1, 2 are the images of some element in G. It is not a monomorphism, and I will leave that to you as a quick exercise to prove that it is not in fact injective. Now, let phi to be another map that we have defined to go from H to G. So it takes an element from Z3Z and gives you back the same element but in Z12Z. This map is not well defined because, for example, 1 mod 3 is equal to 4 mod 3. So 1 mod 3 is congruent to 4 mod 3. But if we apply phi on 1, we get back 1 mod 12. And if we apply phi on 4, we get back 4 mod 12. And mod 12, these numbers are not equal. So we've just proved that phi sends a single element to two different elements, which is 1 mod 12 and 4 mod 12. So in fact, phi cannot be a well-defined map. So it is not a homomorphism because it's not even a map. It's not well-defined. And this is the representation for G and H. And in this case, we would go from H back to G. So for example, we'll start here. 0, it goes to 0. 1, it goes to 1. 2 goes to 2. So we have covered all of H already. But notice here that 0 goes to 3. But that is just nonsense because we've already defined that 0 goes to 0. So it can't go to 0 and go to 3 at the same time. So that is not well defined. Okay, now we've seen a lot of examples on homomorphisms. We know what can be a homomorphism and what can be an isomorphism and what cannot be even a well-defined map. So let us now move on to some properties that homomorphisms can bring about. So the first proposition says that let phi going from G to H be a homomorphism, then phi sends the identity of G to the identity of H. And the second result is that phi of the inverse of G is equal to the inverse of phi of g for all g in g. And lastly, we have that phi of g to the power n is equal to phi g to the power n, again for all g in g. And the proof will be in my next video, lesson 7.1, coming soon, which I hope that you will stay tuned for. Now, let us define some very important subsets of G and H, where phi is a homomorphism going from G to H. The kernel of phi is this set, which we call Ker. Phi is the subset of G, so all the G in G, such that phi of G is the identity in H. So this is a subset of G containing all the elements in G that phi send to the identity in H. The image of phi is just the image of phi, as we've known from linear algebra or from any course in discrete mathematics. It's the set of H in H such that there exists some G in G, such that phi of G is equal to H. So basically an element in H that has some pre-image. So now that we have defined these very interesting special subsets of G, we were going to be proving a lot of stuff about these two subsets. But first, we will start with lemma 1, which says that if phi is a homomorphism from G to H, then phi is injective, so a monomorphism, if and only if Ker of phi contains only the identity element of G and no other element. Again, the proof of this lemma is going to be provided in the next videos. Now, for the example, consider again the homomorphism, the determinant of the matrix. So the kernel of this determinant is the set of all the matrices such that the determinant gives you the identity element of the multiplicative group with identity element is 1. So all the matrices where the determinant gives you 1. And if you have noticed, this is exactly the definition that we've seen before, SL to R. We've seen this in lesson 6. It's the special linear group of order 2 with coefficients in R. The last topic of discussion covers the properties of isomorphic groups. This proposition is very important because it enables us essentially to determine if two groups are non-isomorphic. Usually, it is much easier to prove that a group is non-isomorphic to another group than to prove that they are isomorphic. Because to prove that two groups are isomorphic, you have to, in most cases, come up with an explicit definition of a map between these two groups. You have to prove that the map is well defined, that it's a homomorphism, that it's injective, and that it's surjective to get the result you want. But if you want to prove that they are non-isomorphic, it is much easier using this proposition, which says that if two groups are in fact already isomorphic, then necessarily, first of all, the order of the first group is equal to the order of the second group. G is abelian if and only if H is abelian. Remember, abelian means commutative. And lastly, the order of any element G in G is equal to the order of the image of G by phi in H for all G in G. The intuitive meaning behind this is that isomorphism essentially means that the two groups are the same, have the same structure exactly, just the labeling is different. If they have the same structure, then they should have the same exact properties, in particular, these three properties. The proof of this proposition, again, will be in future videos, so stay tuned for that. Let us now put this proposition immediately to use. The first example says that S3 is not isomorphic to Z6Z. Even though both groups have order 6, so both have order 6, they both contain 6 elements, we have that Z6Z is abelian while S3 is not. And I will leave that explicit proof to you as an exercise. The next example says that D24 is not isomorphic to S4. So let us use the proposition again to say that both groups, even though that both groups have order 24, so we cannot use that fact to say that they're non-isomorphic. We'll have to use something else. We can see that both groups are abelian, are non-abelian in fact, are non-abelian. So we cannot use that fact either. So we'll have to resort to the last one, which says that D4 contains an element of order 12, but S4 does not. So D24 contains an element of order 12, which is R, because R to the 12 is equal to 1 in D24, but S4 does not. Because remember, S4 is the set of permutations of 4 elements, so the maximum order that we can have is 4. We can have 1 cycles, we can have 2 cycles like 1 and 2, we can have 3 cycles, and we can have 4 cycles like this, but not more than a 4 cycle. So this is another example. Another example of a non-isomorphism is left as an exercise, which says that the additive group of real numbers is not isomorphic to the multiplicative group of real numbers. So I invite you to revisit the proposition and use one of these results to say that these two groups are non-isomorphic. Hint, it's part 3. We have another example here that says that the symmetric group of order n is not isomorphic to the symmetric group of order m if n is not equal to m, because in that case we would have that the order of Sn is not equal to the order of Sm. And also we can use the third property, because if n is not equal to m, then there is let's say for example n is less than m, then there is an element of order m, so an m cycle, but there is no m cycle in Sn because m is bigger than n. The last example and the last point that I would like to cover in this lesson is the fact that the additive group of Q is not isomorphic to the additive group of Z. And to do that, we will not be using proposition 2. We will in fact be using a somewhat of a non-trivial argument here. We will be using a proof by contradiction. So proof by contradiction. So suppose Q plus and Z plus are in fact isomorphic. If they're isomorphic, then there exists some phi here, an isomorphism that goes from Z to Q. And in fact, it's an isomorphism, and this is the symbol for isomorphism. So phi is an isomorphism, and we will be using this fact to reach our contradiction. Let us consider the element in Z1. So phi of 1 is equal to some rational number in Q, some a over b, where a and b are integers. So since phi as an isomorphism is surjective, there exists an integer n such that phi of n is equal to a over 2b. So a over 2b is some element in Q, and because phi is surjective, there must be some n in Z such that phi of n is equal to a over 2b. Moreover, phi of 2n, so basically this is n squared, so n squared, but the squared here is additive. So it's written as 2n. Remember, the multiplication here, 2n, just means the element times the element plus itself. So this is equal to phi of n plus n because the operation is plus. So this is equal to phi of n plus n is equal to phi of n plus phi of n, because phi is a homomorphism because it's an isomorphism, and phi of n is equal to a over 2b as previously mentioned over here, and a over 2b, and this is equal to a over b, but we've already said that a over b is equal to phi of 1. So in conclusion, we've said that phi of 2n is equal to phi of 1. Now, because phi is an isomorphism, phi is injective. We're really using all the properties here. We use surjectivity, we use homomorphism, and now we're using the fact that it's injective to say that, well, injective, what does that mean in general? If phi of x is equal to phi of y, that means x is necessarily equal to y. So that means because phi of 2n is equal to phi of 1, 2n is equal to 1. And n is assumed to be an integer. So does there exist such an integer that if you multiply it by 2, you get back 1? No, there does not exist any integer like that here. So what I said is there does not exist any integer n such that 2n is equal to 1. So we have said that because phi is surjective, there exists an integer, and we followed a set of logical rules to say that there does not exist an integer. So something that exists and does not exist at the same time is a logical impossibility and therefore a contradiction. And the contradiction all stemmed from the supposition that q plus and z plus were isomorphic. So it follows necessarily that q plus and z plus are not in fact isomorphic, and with that we have proved the fact that these two groups are non-isomorphic. We have terminated now the lesson 7 in homomorphisms. I really appreciate you sticking this long. I will be posting more next time. Please stay tuned and please like, subscribe, and have a nice day. Bye.